All right, let's take a look at chapters 19 and 20, which are going to be star formation and evolution. All right, the stages of evolution start with a gas cloud. This is just a random cloud of gas, which sort of exists everywhere in the universe. The interstellar medium or the intergalactic medium, which is what exists between stars for interstellar or between galaxies for intergalactic, is just a gas. If the gas is evenly distributed everywhere, or has the same density, or is homogeneous, which are all different ways of saying the same thing, then stars won't form. But if there are certain places in a gas cloud where gas is clumped a little bit closer together, that tighter clumping, that higher density piece of gas will have more gravitational attraction than the gas around it, and it will start collapsing in on itself. Okay? As that gas starts collapsing in on itself, its temperature will increase. All right? Eventually, it will form a protostar, which is the second stage. As it accumulates more and more and more mass, and the temperature starts to rise, eventually at the core, hydrogen will start to burn. For a brief period, the star will be in what's called a pre-main sequence stage. Now, hydrogen is burning, which is typically how we classify main sequence stars, but the star won't quite have finished its maturing process. It'll be fidgeting with its size a little bit, its core will be fidgeting a little bit, changing its size, getting bigger, getting smaller, and then it'll finally reach its main sequence stage, nice, healthy, happy where it is. Okay? Then we have the death stages, the post main sequence stages of the star. So stages 1 through 4 here are all of the stages of the birth of a star, right? Stage 4 is technically its lifespan. Stage 5 encapsulates all of the death stages of the star. Okay? The gas cloud formation occurs through a process called fragmentation. All right? If we start with a gas cloud indicated in the figure on the left, that gas cloud will have regions inside of it where the density is slightly higher, where the gas is slightly more packed slightly closer together. Okay? Those patches of increased density will fragment, will cause the gas cloud to fragment. All right, in the middle of this figure, you can see that there are 4 fragments from that original gas cloud. Within each of those fragments, there will also be little pockets of higher density, which will cause further fragmentation of that gas cloud. And it'll continue fragmenting, continue fragmenting, continue fragmenting. Okay? This gas cloud originally can be humongous. It can be gigantic, way, 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 way bigger than a star. So fragmentation might have to occur many, many, many times before you end with a star. Okay? Not all of these little pieces that are left over will form stars, but some of them will. Something that we're going to talk about a little later is what processes can kickstart fragmentation. Remember that fragmentation will only occur if the gas cloud is not perfectly evenly spread, if it's not perfectly homogeneous. So any process that can produce these pockets of increased density, these inhomogeneities in the gas cloud, those will kickstart fragmentation. All right, so we'll see things like shock waves passing through gas clouds. Those shock waves will compress the gas in certain places. That'll produce these pockets of increased density. That'll kickstart fragmentation. This is sort of the general view of how a pre-main sequence star is formed. Okay, we start all the way to the left with just a gas cloud that is going to fragment. The second stage from the left is a gas cloud that is starting to heat up. You can see it starting to glow. That light is just regular black body emission. That light is not coming from any fusion at the center because fusion has not started to occur yet. The third stage from the left is the protostar. A protostar is characterized by this flat accretion disk around it, which we've talked about accretion disks before. Basically, the gas can only accumulate in the star, which is at the core of this, the very, very bright spot at the center. Gas can only accumulate in the star so quickly. So gas is typically parked around that core, waiting for its turn before it can be accumulated into the star. Because the star is going to be rotating, that spinning actually flattens what would normally be a spherical sort of accumulation cloud. It flattens it into an accretion cloud. It flattens it into an accretion disk. The accretion disk is very, 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 very hot. So it glows and emits a lot of black body radiation. And something that commonly occurs with accretion disks is the formation of jets. Okay? You can see the sort of lightly blue colored cones that are coming out of the top and the bottom of the accretion disk. Those are plasma jets. All right? After everything has accreted onto the star and the star has gained all the mass that it's going to gain, it will become a pre-main sequence and then a main sequence star, which is going to be the last phase all the way on the right. At the bottom is roughly how long each stage takes. So you can see that the fragmentation process takes 2 times 10 to the 6 years. 10 to the 6 is a million, so that's like 2 million years. The collapse of that gas fragment into a protostar takes 3 times 10 to the 4 years. 10 to the 4 is 10,000, so that's 30,000 years. The protostar lasts 10 to the 5 years, which is 100,000. And then the main sequence star will last 10 to the 7 years. All right, which is 100 million years. 10 million years. That really heavily depends on how massive the star is. Very, very massive stars will take much shorter amounts of time than very, very light stars. All right, here's more about the protostar structure. Like I said, there's an accretion disk. The protostar is the actual glowing sphere at the center. And then you have jets. Okay, these are just some actual observational images of what we imagine are protostars actually developing. This HOPS 383, you can see in the Spitzer 2004 image, so the upper right image, that there is just a very, very dim dot. Okay? And then in the Spitzer 2008 image, the lower right image, all of a sudden it's glowing extremely bright. That's because in 2004, this was just a moderately hot gas that was undergoing collapse after it had fragmented, so it's very, very dim. But below it in 2008, all of a sudden it's now in the protostar stage. It's glowing very, very, very bright from the extremely hot accretion disk. Or possibly the jet is pointing at us, which is also extremely bright. Either way, it's going to be much, much brighter than it was in the stage of just the collapsing gas. This might be a direct observation, literally just an image of a protostar, because it looks like there is an accretion disk around a glowing sphere. All right, but we don't know. This is just an image that we think is one of the first direct observations of a protostar, but we don't know for certain. So I'd already talked about this, how a protostar transitions into a pre-main sequence star. Protostars have that accretion disk around them, so they are still accumulating mass. Because they're accumulating mass, the gravitational pressure is constantly changing, so they're unstable. Okay? Their size and their temperature is going to change as more mass is added onto them. As more mass is accumulated, right, and the gravitational pressure increases, the core is going to continue to get smaller. Eventually, it'll spark hydrogen fusion, assuming that enough mass is accumulated. Remember that if a protostar, or if any star, doesn't actually gain enough mass, it will never become a true star. It'll never get hot enough to burn hydrogen. Those stars that don't accumulate enough mass to burn hydrogen are called red dwarfs. Okay? The pre-main sequence stage is this third bullet point where it says as soon as hydrogen is burning, now all of a sudden you have this massive thermal pressure outwards combating gravitational pressure inward, causing it to increase in size a little bit. With the increase in size, the temperature drops, so the thermal pressure drops. Gravitational pressure inward might collapse down a little bit. It's going to sort of sputter, increase its size, decrease its size, just rapidly fidget a little bit until it gets to its happy equilibrium state, which is going to be when it's a main sequence star. Now, the accretion disk will be lost through two processes. Either the star absorbs that gas from the accretion disk that's waiting, or the star literally blows its accretion disk away. The reason is that you have to remember when fusion is occurring, that star is emitting a wind. Okay, it's emitting all of this electromagnetic radiation, this particle radiation off of its surface. We talked about the solar wind, the wind from the sun, which comes and hits the Earth constantly, which we're protected from because of our magnetosphere. But the accretion disk is exposed to the stellar wind, and that will literally blow the accretion disk away. We can see this in images D and E, that the accretion disk is asymmetric. It doesn't look like a circle because the stellar wind is literally blowing the accretion disk away. These are what HR diagram paths look like for stars of various masses going onto the main sequence. So something that this indicates, you can see on the right hand side, it indicates for each path what the mass is. Half a solar mass, 1 solar mass, 2 solar mass, 5 solar mass, 15 solar mass. You can actually see that the time for each of these birthing processes is shown for each mass. So that half a solar mass star takes 100 million years to complete the birthing process and reach the main sequence. One solar mass star takes 30 million years. That's how long the sun would have taken to complete its birthing process and reach the main sequence. But a 15 solar mass star only takes 0.16 million years. So something like 1/5 of a million years, or that's actually 160,000 years. It's probably easier to say 160,000 years to reach the main sequence. You can also see that for a larger mass, when it's on the main sequence, it's at a higher temperature. As the mass increases, it's further to the left on the main sequence. Further to the left is at a higher temperature. It's also higher on the main sequence for a larger mass. Higher means it's brighter, it has a larger luminosity. Okay? That birth line is the point at which it becomes a pre-main sequence star. When it transitions from the protostar to the pre-main sequence star, that's when hydrogen burning occurs. It's not quite a main sequence star because remember that pre-main sequence star, once hydrogen burning occurs, it's fidgeting and fighting to reach equilibrium for a short amount of time before it finally reaches the main sequence. Oh, this image is pretty blurry, but this is a table that shows a bunch of different characteristics of the gas that will eventually become a star. It's not technically a star when it starts, but the gas that will eventually become a star through the various stages of stellar birth. So stage 1, when it's just a cloud, right, has an extremely low central temperature and surface temperature, 10 Kelvin. That's very common for like interstellar medium. It's extremely cold. 0 Kelvin is absolute zero. You can see that the density, 10 to the 9 particles per cubic meter, is the lowest that it's going to be. As it progresses to a cloud fragment, to a protostar, when it says star here in stage 6, it means a pre-main sequence star. You can see that the temperature is increasing from 10 to 100 to 10,000, all the way up to 10 million by stage 6. The particle density is increasing from 10 to the 9 particles per cubic meter to 10 to the 31. It's getting smaller in diameter. In stage 6, the temperature is 10 million Kelvin, which is not high enough for hydrogen fusion to occur. Hydrogen fusion occurs at 14 million Kelvin. You see by stage 7, when it reaches 15 million Kelvin, now hydrogen fusion occurs. It doesn't actually say, I don't think that I included it here. It doesn't say what the mass of this star is, but I'm assuming that this is around the mass of the sun. Because if you look at the little footnote at the bottom, it says round numbers. For comparison, recall the diameter of the sun is 1.4 times 10 to the 6. So the diameter of this star is 1.5 times 10 to the 6. So I'm assuming that this is a solar mass star. So like I said, what conditions are going to lead to stellar birth? Those are going to be the conditions that tend to produce fragmentation in gas clouds. What conditions are going to lead to gas clumping together within a cloud? Typically, shock waves are going to be the kickstarter of stellar evolution. Shock waves are going to be produced through two very important processes. The two most important processes are going to be dying stars. When stars die and they explode, we'll talk about stellar explosions later. Those stellar explosions, supernova or regular nova or hypernova, those will produce shock waves. The shock waves will compress the gas. That compressed gas will kickstart fragmentation. A second really important method will occur in spiral galaxies like the Milky Way. On the spiral arms of a galaxy, which are basically shock waves that are rotating around the center of the galaxy, you will see a lot of brand new stars that are being born. Because as the spiral arm passes through the gas of the galaxy, it will compress the galaxy, kind of like a propeller in water. Okay? As that spiral arm passes through the gas, it's going to compress the gas, which will kickstart fragmentation, kickstart stellar birth. So here we can see in a nebula, which is typically the remnants of some sort of stellar explosion, in the center of this image, where the dark non-colored part is, that's where the explosion would have originated. Where all of the red color is sort of diffuse around that dark spot, that's where the shock wave is right now. And you can see massive amounts of stellar evolution at the bottom. Those are what the blue dots are. Those are very, very young stars. So I've mentioned brown dwarfs before. I just realized that earlier in this video I had said red dwarf when I meant to say brown dwarf. Earlier in this video, you guys can rewind it to see what I mean. I had said that if a star doesn't accumulate enough mass to kickstart hydrogen fusion at its core, it will be a red dwarf. That's incorrect. I meant brown dwarf. A brown dwarf is a star that never accumulates enough mass to kickstart hydrogen fusion. So it's technically not a star. It's technically just a gas cloud. Okay? Brown dwarfs occur if a gas cloud accumulates less than 10% of the sun's mass. Okay? It's usually about 8% or 0.08 times the solar mass. It will never have enough gravitational pressure to compress the core enough to reach 14 million Kelvin in the core. Okay? In this image, we can see a red dwarf. A red dwarf is the coldest true star. So hydrogen fusion occurs in a red dwarf, but it is the coldest true star. So it's consequently the least bright true star. But you can see how bright it is in this image compared to the brown dwarf. The red dwarf appears to be this massive glowing orb. The size of the red dwarf isn't actually as big as it appears to be. It appears to be this big because it's overwhelmingly bright. The brown dwarf appears to be this tiny dim dot next to the red dwarf. These are lifetimes on the main sequence and brightnesses and central temperatures for stars of various masses. If we look at Proxima Centauri, its central temperature never got high enough for it to be a true star. If we look at Proxima Centauri, it has a central temperature of 0.6 million Kelvin or 600,000 Kelvin. That's not high enough for it to burn hydrogen. So it's actually a brown dwarf. If you look at the luminosity is tiny. That is 0.6% of 1% of the sun's luminosity, or 6/1000th of 1% of the solar luminosity. It's so dim Because fusion never occurs. The sun, right, which has a center temperature of 15 million Kelvin, which is above that minimum of 14 million Kelvin. It has a brightness of 1 because it's measured in solar luminosities, and it's going to last 10 billion years. The lifetime on the right is given in millions of years. So 10,000 million is 10 billion. It's going to last 10 billion years on the main sequence. But look at Proxima Centauri, that brown dwarf. It's going to last 16 trillion years on the main sequence. And then as the masses get higher, all the way up to Spica B, it's going to last 90 million years. So something like 1,000 times less, or 100 times less, technically, than the sun, because it's 7 times more massive. All right? Now, what happens when a star leaves the main sequence? This is what we're going to talk about in the next lecture.